In this video, we are going to consider the question, how does the electric potential behave in a uniform electric field? We know from our study of electricity that the uniform electric field is probably the simplest one to deal with mathematically because it has the same strength everywhere and the same direction everywhere. And so what we're going to find is that the electric potential is also going to change in a very simple way. And so our goal here is to figure out what that way is. So I'm just going to remind you that if you have a uniform field, an E field, and you place a charge into it, say plus Q, that charge is going to experience a force which is always going to be pointing in the direction of the electric field. Okay, so it's a constant force, and the magnitude of the force is going to be equal to the value of this charge multiplied by the magnitude of the electric field strength. And so the nice thing about this is wherever you put this charge in the field, it's always going to have the same size force and the same direction force acting on it. And so that's what we mean by a uniform field. So why don't we take a look at some different cases here in the picture underneath. And we're going to look at cases where you take a Q and you're going to move it and allow it to move in different directions, either with the electric field or opposite the direction of the field. Okay. And what we're going to do is try to understand how much work is done in each case, what's the change in potential energy, and finally, what's the change in the electric potential. So let's look at the first case in which the charge moves with the field. So the charge is going to have a displacement which is going to be heading down because the electric field direction is down. Okay? And also the force on that charge is going to be downwards. I'll just label that F. Okay? And that's because the electric field is going down. Okay? So you've got a positive charge plate up here, negative charge plate down here. Again, the field lines are pointing down, so the electric force is also going to be going in that same direction. So how much work would be done by the field in this case? Well, the work will be positive, first of all. It's positive because these two vectors are in the same direction. And it's going to be positive Q times E times D. And that's because QE is the force and D is the displacement. So work is equal to force times displacement. Positive because these guys are in the same direction. Alright, so if we know that, then we can immediately say that the change in potential energy is equal to negative QED. And that's because the change in potential energy is always the opposite of the work done by the force, the conservative force. So these two things are opposite. Okay? That's how you figure these things out. So then what would the change in potential be between your starting point and your ending point? Okay? And the change in potential is simply going to be the change in potential energy divided by Q. So if I divide Q out of this expression up here, I'm going to end up with negative E times D. And the meaning of that is going to be that the potential is decreasing as I go from this direction to this direction. So I'm going to say, I'm not quite sure how to represent that here, but as I go this way, I'm just going to make a note that the potential decreases. So as I'm moving with the electric field, my potential energy is going lower and lower, and my electric potential is going lower and lower. So the volts would be going lower and lower, right? Because this is measured in volts. Now, the expectation would be that if we go and we take our charge and we move opposite the electric field, that these things should flip. So maybe I take this charge and I somehow raise it in this field. Maybe I shoot it out of a gun, maybe I have someone pushing it. For whatever reason, I'm going to make it go up. It's going to be in the opposite direction of the electric field. While that's happening, the electric field is going to be pushing it in the downwards direction. And so now you have a force one way from the field, and you have a displacement in the opposite direction. That's a recipe for negative work. It'll be equal to negative Q times E times D. And so this negative work by the field is going to cause an increase in the potential energy, equal to plus QED. And therefore, the electric potential should be a positive change. So when I go from here to here, I would be increasing the electric potential. Okay. So there's this guy named Ed who keeps showing up here. Ed is electric field times the displacement parallel to the field. And basically, Ed is the difference in potential between your starting point and your ending point. And so if you're starting up here with a positive charge and you move with the field, the potential drops by Ed. It's a negative ED. If you're starting down at the bottom and moving up, the potential is going to increase by Ed. That's your plus ED. And that's a pretty important thing. So the change in voltage in a uniform field is going to be equal to Ed. You can go through and you can also check this out for negative charges. So if I put a negative Q here and a negative Q, if I allow this negative Q to go this way, opposite the electric field, what's going to happen is that I'm going to have a change in potential. But because this charge is negative, the electric field actually pushes it up. So in this particular situation, the field does positive work on that charge as you go against the field. And that means that the potential energy is going to decrease. And that means that the electric potential would be also decreasing as I go in that direction if I divide out the Q. So again, if my charge moves from here to here, the electric potential is changing by Ed, and I'm going to a higher potential here. Okay? So this is my high potential. This is my low potential. And that's exactly the same as what we had before, where we had a high potential here and a low potential there. Okay. I realize I might have made a little bit of a sign mistake here, in the sense that when this charge is negative and you divide out a negative Q, that was my mistake here. If we divide out a negative Q, this becomes positive. So I'll make a note, divide by negative Q to get that positive change. So that makes sure that when you're going in this direction, you have an increase in the potential. Let's do the last case here. Negative charge goes down, force goes up. In this case, you would have negative work done by the field. The change in potential energy would be an increase, so that's positive QED. But if you divide, again, by negative Q, you end up with a decrease in potential. So the long story short is whenever you move with the field, the potential is going to decrease. Okay, there's a little bit of a trick here because you're dividing it by negative Q in these two cases. So the big lesson, let's summarize, is that when you move with the direction of E, the potential will decrease. By ED. Or I suppose you could say by negative ED because it's decreasing. And when you move against E, the potential will increase by that amount. So I'm just going to write vice versa. So if you move against the electric field, the potential will increase, and it increases by positive ED. So that's the main lesson from this. Okay. So have we answered the question? I hope so. Potential behaves in a very simple way. It changes by ED when you're in a uniform field. Of course, if you go against the field this way, that's the direction of your displacement, then there is no change in potential, right? Or you could say that delta V is equal to 0 because you're really not going with the field or against it. So that's probably a good thing to also put in here in your notes. All right, so on the flip side here, just a couple of quick examples of how you can use this. Let's say that you've got a voltage difference of 300 volts, and these plates are separated by 0.03 meters. I'd like you to, we can go ahead and find the electric field strength and determine voltages at different points. So the first thing we'll do is find the field. The electric field is going to be equal to the change in the potential divided by the distance. And in this case, I'm going to use D as the distance between the plates. So that's going to be 300 volts divided by 0.03 meters. And that's going to be 10,000 volts per meter. Okay. And so, by the way, this is the first time we're seeing that the units of volts per meter can be used for expressing the electric field. I will tell you that volts per meter are equal to newtons per coulomb. I'll put that in parentheses. And you can check that with a little bit of unit conversion bits. So I'll leave that to you to check it out. All right, so what you have here is 10,000 volts per meter. That's the potential. If you were to take this gap and divide it up, if we were 0.03 meters apart to begin with, that means we're 0.01 meters apart if we divide this gap into 3 parts. Now, the reason I'm doing that is just to make the point that every time you go forward by a certain distance, the voltage is going to change by the same amount. So if I go from A to B, my difference in voltage should be equal to E times D, and it should be increasing because I'm going against the field. And so it would increase by 10,000 times a distance of 0.01, and that means it's going to increase by plus 100 volts. So going from A to B will cause the voltage to increase by that much. Now, if I go from B to C, it'll increase by another 100 volts. And when I go from C to D, it'll be another 100 volts. And so the idea is that if you say that the voltage at point A is equal to 0, then you can just kind of add on 100 volts to figure out the voltages at the other 2 points, or the other 3 points. Okay. And so that's really simple to do, because the voltage is just increasing in a linear way as you move across the field, or move with, I should say, move against the field. Sometimes you'll talk about, this may seem a little bit strange, but it may also be possible to say that what if we define one of these other plates, what if we make this side 0 volts, right? And you might wonder how that's possible, but voltage is kind of funny. It's just a reference point. It's completely arbitrary. So instead of making